So I think we're just about ready to get started then. So thank you everyone for coming out to listen today. My name is Rohun, and I'm the Vice President of the Michigan Aeronautical Science Association, also known as MASA. We're the student rocketry team at U of M. And today, Hunter, Eric, and I are going to be presenting our current rocket called the Tangerine Space Machine. So we're building the Tangerine Space Machine as part of a competition called the Base 11 Space Challenge. It's a competition for $1 million prize to be the first student team to launch what's called a liquid bipropellant rocket past the edge of space. So this has been a multi-year endeavor. We've been working on it since I think 2018, and we're planning to finally launch in December 2021. So we're getting excited as we move into our manufacturing phase, and we're excited to share some of that with you today. So in the next few slides, I'm just going to give a quick overview of the Tangerine Space Machine, or TSM as we call it. So our rocket is 26 feet tall. It's a single stage rocket. And as I mentioned, it's a pressure fed liquid bipropellant rocket engine. So we have two propellant tanks, one for RP1, which you can see over here, and one for liquid oxygen, which you can see here. These tanks are actively pressurized to 650 PSI during flight. And the propellants are fed through a system of tubing down to our engine, which you can see in the top right corner here, where combustion occurs, and that generates thrust for our rocket. Our rocket body is an all-metal airframe. It's largely aluminum. There's some bits of steel and titanium in there as well. We also feature a full autonomous parachute recovery sequence too. So today we're going to go into depth on each of the technical subteams that make up this rocket. Before we get there, there's a quick diagram here of our mission concept of operations, or mission CONOPS as we call it. So we're going to launch from Spaceport America in New Mexico. Our engine burn is going to last for around 41.5 seconds. And we do have over 850 pounds of propellant aboard our rocket, which makes up more than 60% of the rocket's wet mass. So after engine shutdown, we're a lot lighter. We reach the Kármán line, which is defined as the edge of space, around 2 minutes into flight. We have payload deployment, and then our Nosecone separates at 2.5 minutes. After that, we have a series of 3 parachutes, which are deployed to guide our rocket back down to the ground. And we land at the White Sands missile range around 9 to 10 minutes after flight, or after launch. A couple key statistics: we do hit Mach 5 during flight. Our mean sea level thrust is over 4,000 pounds of force, and our descent velocity at the end is 11 miles per hour. So it's a nice soft landing. So now I'm going to give a quick overview of some of the major structures that make up TSM. So one of the most complex ones that we have is our propellant tanks. As I mentioned, these are pressurized to 650 PSI during flight, and they're designed to a safety factor of 1.5. So we do destructively burst our propellant our prototype propellant vessels, and this is to make sure that our manufacturing is up to spec. So you can see a picture of our burst test happening over here on the right-hand side. And as far as the components that go into this, our propellant tanks are made out of rolled aluminum tubes. They have anti-slosh baffles that are welded to the interior, and you can see a picture of that in the bottom right corner here. We also feature anti-vortexing baffles at the bottom of each tank. We have 2 end caps on each tank that have their own plumbing ports, and we also have coupling rings on each end cap to connect the propellant tanks to our airframe. So one thing to note right now is we are completing our final prototype tank. We plan to test that later this month, destructively, and then if that survives to strength, then we're going to begin designing our flight tanks, or producing our flight tanks. So one of the other major things is our airframe. So in between our propellant tanks, down here, we have an airframe section called the inner tank bay. That houses some of our plumbing for liquid oxygen and RP1, which is the fuel that we use. Our second airframe section is called the helium avionics airframe, and that's located up here. It's above the liquid oxygen tank and below the Nosecone. And in here we have our helium pressure vessel, as well as some plumbing for that and our LOX tank, as well as our avionics mounting structures. So the helium avionics airframe is the largest component on TSM. It is manufactured out of house due to its scope, but it's assembled fully in-house. And one thing to note for all of our airframe sections is they are built and designed with these removable panels. This allows us to have access to the avionics or the plumbing that's stored inside of the airframe. One of the final main structures that we have on TSM is called the thrust transfer structure, or the TTS. So this utilizes an aluminum and stainless steel welded design. It has a pretty elegant system of rods, tubes, and clevises to connect the engine to the bottom of our rocket. The goal of the TTS is to transfer engine thrust directly into the rocket body. So our TTS has to survive over 4,000 pounds of force, and it has to direct the thrust straight into the rocket. We can't have the thrust going at an angle because we need to have stability for our rocket. So we have done some really exciting testing with this recently. We did a single rod crush test for one of these guys that you see on the right side. That was a proof of manufacturing, and it proved the need for heat treat after welding them. We also did a full TTS crush test recently, which you can see here in the bottom right corner. Our TTS survived to over 9,000 pounds of force, which is a safety factor of 1.8. The failure mode was nominal, so we've deemed this acceptable for flight, and we're now completing manufacturing of our final TTS. So now I'm going to turn it over to Eric to discuss some of our propulsion systems.
Yeah, so our propulsion sub-team right now is working on two main rocket engines. The first being our experimental engine, PT-163. You can see the Hotfire for that in the middle of the screen there. And this engine has helped us develop all of our ground support equipment, while our main engine, RPD-2, our main flight engine, is currently being designed and getting into preliminative manufacturing. You can see RPD-2 on the right side there, nice and catted up. But the only part that we actually have in-house at the moment is the nozzle, which you can see on the bottom right there. The actual engine itself will be 3D printed in Inconel, and this allows us to have a more complex contour on the inside that allows regenerative cooling all the way from the bottom of the nozzle up through the top of the injector, which is on the top right. Now, the main propellant valves are a big thing of propulsion. These are essentially the go buttons for a rocket engine, and we have two main propellant valves. The first being the fuel valve, that's version number 3 on the bottom right there. Currently, we're using version number 2, but this one is our flight optimized valve, which is going to take all the things that we've learned from the previous 2 versions and hopefully make that the best design possible. This valve is made out of aluminum, and that allows us to manufacture it quickly in-house, and we've been able to do that cheaply and effectively. Now, the LOX valve, on the other hand, is made out of stainless steel, and we have worked on only one version because it is much more complicated than our fuel valve. This is because LOX is both a very, very potent oxidizer as well as cryogenic. I think it's like 90 degrees Kelvin. So it has a lot more in it to actually be able to seal properly and prevent issues. Now I'm going to talk about the Assembly, Test, and Launch Operations team, or ATLO for short. The main part of ATLO, at least right now, is our Hotfire testing. And we do this through use of our ground support equipment. So you can see a bit of our setup there. Like on the top right, we have our tank stand, which has LOX on the right side of it and fuel on the left side of it inside tanks. And I think you can kind of see one of the tanks in the center picture. But these tanks are pressurized and filled up by a CNG or COPV. Okay, we will use a COPV for flight. And right now we're using a CNG tank because that's just a big steel thing that holds air pretty well. So it's a lot easier to pressurize that. But on the bottom left there, you have the fill system, and that allows us to load our liquid oxygen and chill in our system using liquid nitrogen, as well as allowing us to remotely fill, drain, and vent our COPV. Now, a big part of ATLO is the pressure control, because when you're launching your rocket, you don't want to have a blowdown test where the pressure is like fluctuating as you're going up. You want to have a constant pressure with a constant thrust, or be able to change that pressure while you're going up. So we have our TPC system, or tank pressure controller, which uses a closed loop PID controller in order to eventually kind of approach our target pressure. So this was one of our preliminative tests, and we had a target pressure of 80 PSI. And as you can see, it kind of dipped down at first. That's the initial opening. And then the actual system, which is a needle valve attached to a motor, is opened and closed, allowing a certain amount of helium into the tank in order to keep a constant pressure. Now, ground support equipment's great, but eventually we have to take all of this and we have to put it on a rocket to send up. So we do this by putting it into separate bays on the actual rocket. I know Rohan talked about this a little bit earlier, but This is our fluid and propellant delivery system. We have 3 main bays, the first being the engine bay, which is at the bottom of the rocket, and that has all engine plumbing, the main propellant valves, the purge systems, and the emergency thrust termination, which I think Hunter's going to talk about a little later. And then we have the inner tank bay, which has our tank pressurization, our level sensing equipment, and safety devices, and that's between the fuel tank and the LOX tank. And then up at the top of the rocket, right underneath the helium tank and above the LOX tank, we have our helium bay, which is similar to the inner tank bay, but it has extra isolation valves for the helium, since that's what's mainly up there.
Awesome. Now I'm going to talk a little bit about the avionics sub-team that works on our rocket. So avionics is really concerned with everything that's controlling our rocket during tests and during flights. And this is split into three main areas during those physical tests or the flight. We start with mission control. And that's where all of our people who are running the test or the flight are sitting. We've got computers there and a data server, and we can link to the launch site and the rocket through radios and wiring to the launch site. At the launch site, we have various tanks that have propellants in them or helium to pressurize our tanks on the rocket or during a test. We also have batteries and ground support equipment that Eric talked about during the Athalye section. This is connected to our rocket or a test stand through quick disconnects. So that way, when the rocket does take flight, those can be disconnected and the rocket is untethered from the ground and can fly away autonomously. On the rocket, we have a bunch of different boards that we can see on the next slide. These include things like the engine controller and the pressurization board, as well as the flight computer. The engine controller you can see in the top right here and the bottom right. These are designed in-house by students and then manufactured out of house. And the bottom right actually shows our engine controller at an engine test. So you can see all the wiring that goes into that. On top of boards, Avionics also makes GUIs for students to use to interface with our boards during tests. And you can see that in the middle there. Those are used and constantly being updated for various tests, so we know what's going on with our rocket and can actively control that. If we go to the next slide, we can talk about the third big part of avionics, and that's telemetry and radar, and also flight termination, which is all coupled together. So our rocket has 3 patch antennae on it. Those wrap around the edges of the rocket and allow us to communicate with the rocket in flight. This is mostly just for getting data for us. The rocket is passively controlled, so we don't actively control it while it's flying, with the exception of a flight termination system. So the rocket, as it's flying, uses a GPS and an inertial measurement unit, or an IMU, to check in 2 different ways where it thinks it is. It'll check that with where it should be. And if we're on course, everything's great. But if it starts to veer off course, then the flight termination system will be activated and will shut off that engine. We can also do this from the ground with range radar tracking. So at White Sands Missile Range, which is where we're launching from, they will be tracking our rocket with radar. And if they determine we're veering off course, they'll send the signal to our rocket to terminate the flight and turn that engine off so we don't go anywhere we're not supposed to. But once we reach the top of our flight, the aerodynamics and recovery team really comes into play. That's our final technical sub-team on MASA. And as you might expect, they have a lot to do with the recovery of our rocket. So once we reach the apogee, or highest point in our flight, the recovery system really kicks off. So the first thing that happens is our nose cone will actually separate off the top of our rocket through a separation mechanism. This mechanism is pictured in the bottom right and has been manufactured, and testing actually started up just last week. So we're testing with different springs how we can shoot the nose cone off of our rocket once we're at the top of flight. After that happens, the nose cone falls down under its own parachute, hits the ground really gently. But the rocket is much more massive, so it takes a little bit more to slow it down. We have a pilot chute that is deployed near the top of our flight to keep us oriented properly. Then a drogue parachute, which is 7 feet wide, is deployed around 10,000 feet up. That slows us down from almost Mach 1 to about 130 miles an hour. And then our main parachute, which is 50 feet wide, is deployed, and that slows us down all the way to 16 feet per second, or 11 miles an hour, for us to touch the ground softly. Aerodynamics and recovery isn't just focused on recovery, though. We also do simulations of a rocket using an in-house 6 degrees of freedom flight simulator that we've written in MATLAB. So this allows us to input all the parameters of our rocket, take in live weather data from the launch site where we're launching from, and then plot various trajectories of where our rocket might end up. We also use Monte Carlo variation, so we can test different variations of our rocket, like a slightly off-angle thrust or slightly higher drag than we're anticipating, and then see how that affects our trajectory. The final little component for aerodynamics and recovery is the aerodynamics structures on our rocket. These include things like the Nosecone and the fins, which are both in production right now. So the Nosecone is a big piece of rolled sheet metal, and that has been rolled and is currently being welded out of house. It needs to be done out of house because of how tall it is. It's about 6 feet. And the fins are actually being produced in-house. So they're a sheet metal bent skin with a titanium leading edge and an aluminum trailing edge. And those leading and trailing edges have been CNC'd in-house and are being finished up this week.
Yeah, so now I'm just going to speak pretty briefly about our timeline and launch logistics and the final months of this project. So as I mentioned, we are planning for a late December 2021 launch of TSM. We're currently finishing up some of our testing and manufacturing of the rocket. So right now in production, as Hunter mentioned, we have our fins and nose cone for flight. We're also working on our airframe sections for flight right now. Our final prototype propellant tank. We have some avionics boards in-house already, and some of the others are being brought up at the moment. There's a lot of exciting stuff happening. This summer is going to consist of a flight qualification campaign for the engine, our avionics software, and most of the testing for the structural components of our rocket. There's going to be a lot of work to be done this summer. Launch, as I mentioned, is going to occur at Spaceport America in New Mexico, and we're going to be supported by the White Sands Missile Range, the FAA, and Friends of Amateur Rocketry in California. So we did want to throw in a quick slide here just to thank our sponsors. So we have some incredible industry sponsors. We do design reviews with them. We get some material donations from them, a lot of consultations. And really without them, we wouldn't be able to do what we're doing here with trying to send the first collegiate liquid bipropellant rocket to space. So that just about wraps up our presentation today. If you do want to contact us, please feel free to go to our website. There's a contact page where you can send a message directly to MASA leads. We are also pretty active on social media. And as I mentioned, there's going to be a lot of cool stuff happening in the next few months. So I highly recommend checking that out. We'd also like to thank SEDS today for putting on this symposium. It's been a lot of fun already. It's been great to hear these speakers. So definitely looking forward to the rest of today and tomorrow. And we'll now take any questions if you have any.
All right, thanks, MASA. I've heard like your base 11 liquid rocket talk before, but every time it's always like there's new tests or there's new components in production. So that's really awesome. I wanted to ask, how do you interact with other universities? Like their rocket teams? Do you talk about, what the design is like? And then how do you interact with industry? I know you said you do some design reviews, but that's my question.
Yeah, sure. So there's some teams which are actually controlled by something called ITAR, which is the International Traffic in Arms Regulation. That basically means that the information about their rocket is completely private and they're not allowed to disperse any information about it. So with some of those teams, we obviously don't have too much discussion. There is a giant Slack workspace, which has a lot of the top rocketry teams in the nation, where some of our leads discuss with other rocketry teams across the nation. But most of it is at a very high level. A lot of what we know is from their social media posts. A lot of what they know about us is from our social media posts. With regards to working with industry, we do have a pretty strong connection with a lot of aerospace companies. So we do design reviews occasionally with, Hunter can speak to this actually, with a company called Airborne. I don't know if you want to talk about that real fast.
Yeah, Airborne's a big, one of our sponsors that does a lot of design reviews with us. So the recovery team meets with them once every other week usually. And they're just a parachute supply company that has been working on various things with NASA and other major aerospace companies. So we do short, about half an hour meetings every other week and just present changes that we made in our systems and stuff. This initially started as a large overall design review so we could actually figure out how to land our rocket successfully with parachutes. And now it's more in the weeds of little technical details that you might not find unless you've been in industry for a long time. And it's really, really helpful for all of us. Yeah.
Great, thanks. So Gus in the chat has a question. Do you see this rocket design evolving after the base 11 challenge, possibly implementing turbo pumps, having active control if the government allows it, or creating a launch platform for future experiments?
Yeah, so active control is definitely something that is an interesting concept, but because of the government regulations, we're pretty sure a student team is not going to be able to do that feasibly. There are a lot of ideas for rocket design that we've already been discussing, which we want to implement on future rockets. This includes things like on our propellant tanks, using stringers on the inside so we can make them less thick and take less mass. Things like trying to use different pressurants like nitrogen instead of helium because of the cost benefits. So there's a lot of small rocket design elements that we're definitely going to improve on. With regard to the launch platform for future experiments, that's a really interesting idea. We do have a payload that we're deploying that's built by the blue team at U of M. And we are definitely exploring the idea of creating, using TSM after this launch as sort of a launch vehicle for other payloads from U of M that want to go to space for science.
Sweet. And do you see MASA building liquid engine rockets like long term in the future?
Yeah, so kind of a quick summary. There's two main types of rocket designs. So there's one that's solid propellant. It's essentially a fine powder, which you ignite and it combusts and provides your thrust. That's the most simple type of rocket engine. A liquid propellant engine requires all of this tubing that we saw in this slide about Athalye. So there's a lot of additional complexity from having a liquid rocket design, especially when you're using cryogenics. So we definitely plan to pursue liquid rockets in the future because that's where we can learn the most and push the boundaries of what student teams are doing.
Great. We've got about 4 more minutes left, so we can take a couple more questions if anybody has them. Feel free to put them in the chat. I guess I'll pose the same question to you that I did to MRover. How do you guys handle knowledge transfer from year to year, especially with a project that takes this long to see through? How is that? Has there been folks who have stuck around with it, I guess, even after they've graduated, just to see it to launch?
Yeah, absolutely. There's actually some people who have graduated and they're working jobs in industry. So we have a few former teammates at Relativity Space, Blue Origin, and SpaceX who join our Slack or come to meetings every once in a while to help us out, give us advice. That's definitely like a really important method of knowledge transfer. As MRover mentioned, we're also working on our own documentation. So we have an internal wiki page where we have documentation about all the sub-teams and all the subcomponents on our rocket. And we try to use that documented information because that's the best way to have new members learn and have current members understand systems that they don't have breadth in.
Awesome. Well, thank you all for coming. We really appreciate having you.